Hi everybody, this is the next session in our journey through nuclear physics, SP6f Radioactive Decay. To get you thinking about these, there's 4 images showing different types of radioactive decay. You should be familiar with what those are, and if you aren't, then you need to go back and look at the video and the resources and lesson stuff from SP6e types of nuclear radiation, so make sure you've done that first, please. Okay then, so we fundamentally got the alpha particle here, 2 protons, 2 neutrons, a helium nucleus for that one. This is a beta minus particle, an electron, high energy electron that is emitted from the nucleus. This is a positron, same size and mass as an electron but with a positive charge. And this is an electromagnetic wave, which is the gamma radiation that we should know about. What we really need to consider from these is, what effect, if each of these is thrown out of the starting nucleus, what does it leave behind, and how can we model and calculate what's happened to the remaining nucleus when each of these different types of radioactive emissions have happened. So that's what we're really about in this session. If you're referring to the online textbook, then it's pages 100 to 101. Let's get going. The main learning objectives for this are to balance the nuclear equation, so we can actually add up things like this here and work out what we started with, what gets emitted, and what we are left with at the end. Also explaining how the proton and mass numbers, relative atomic mass and atomic number, are affected by different kinds of decay, and see what happens when nuclear rearrangement happens after particles are thrown out of the nucleus. And in particular, and the perhaps most challenging part of this, is to be able to describe and explain and calculate the process of beta minus and beta plus emissions. To remind you, the unstable nucleus is what causes radioactivity, random process, and it throws something out there, whether it's an electromagnetic wave or some sort of particle. That is radioactive decay, and there's a few technical terms that we need to be aware of as we go through this. Keywords: radioisotopes should be pretty straightforward. It's an isotope of an element that's actually radioactive. Decay, as in with teeth, is the breakdown of something into smaller particles. A nucleon is probably a new word for us, but that refers to a particle in the nucleus. So it's got to either be a proton or a neutron, but nucleon is probably a new word. And when we're talking about decay, we talk about parent and daughter nuclei. We start with the parent, and the product of it is known as the daughter. I'm not sure about the gender assignation of that, but that's how it is, parent and daughter. We start with the parent and then we end up with what the daughter nuclei is, and those are the things we're going to be calculating later on in this session. So we need to know those technical terms, because that's how this work will be referred to when it finally matters. Other points to remember that we should know something about is the atomic number, is the number of protons in the nucleus, and of course, counterintuitively, we represent that by the letter Z, is the atomic number. And the mass number, which I refer to, or the chemists would prefer you to say relative atomic mass, is the number of protons added to the number of neutrons in the nucleus. And naturally, that is given the letter A. So not worried too much about that. It's tend to be later on physics, but I do refer to it in this presentation. Atomic number that you have can be used to look up elements in the periodic table, and I'll have sent you a copy of the periodic table if you haven't got one to hand, because we'll be looking up certain elements of that. It's the atomic number that tells us what it is. Mass numbers can be different, because as we know, there are different isotopes of the same element. But when we look things up, we just look for the atomic number, and if the mass number is different, doesn't matter. It's the atomic number that tells us what element we're dealing with, or what we've produced. Alpha decay then. 2 protons, 2 neutrons. This is how we may refer to it, as an alpha particle like this, or maybe the helium nucleus here. Helium, 2 protons plus 2 is 4, and a charge of 2 plus, because there's no electrons to balance the positive charge of the protons. So that's what an alpha particle looks like. And this is perhaps the easiest thing to calculate when an alpha particle is thrown out of a starting point. Because we have the parent nucleus of whatever we've got, in this case uranium-238 isotope. It decays because it's unstable. It throws out an alpha particle and leaves behind a daughter nucleus. Now we can see the maths here. It's thrown out 2 protons and 2 neutrons. Pretty straightforward to calculate for alpha decay. To highlight that, 2 protons and 2 neutrons, so therefore the atomic number decreases by 2. because 2 protons are thrown out with the alpha particle, and the mass number must decrease by 4 because 2 protons and 2 neutrons are thrown out, and the mass number of the alpha particle is 4. So that is the pattern that we need to be aware of for alpha decay, and that's pretty straightforward to do. You simply take 2 off the atomic number and 4 off the mass number for this. Don't forget, during these videos you can always pause them, replay them and go back if you didn't quite get it first time round. Okay, so the number of protons has changed, and we're no longer dealing with uranium. We are dealing with a brand new element, thorium, here, which has got an atomic number of 90. Look it up on the periodic table. So here's some tasks for us to have a look at, to write the nuclear equations for these elements that have undergone decay. So we've got actinium 223 AC, fermium 243 and platinum 190. We always refer to these things by their mass number. So this is the isotope of actinium, is the 223 mass number version of it. Okay, and if we write that one down, we say, right, actinium is going to go down by 2 because we've got 2 protons going out with a helium nucleus, and the mass number is going to decrease by 4. So we simply go 89 to 87, 223 to 219. Look it up on the periodic table, what's got an atomic number of 87, and it's francium. Okay, so pause the vid, have a go at the next 2. Okay, I'm going to reveal the answers to the other 2 then. So fermium 243, similarly, fermium's got an atomic number of 100, 243 is the mass number isotope, alpha particle is given off, so therefore the atomic number reduces by 2 and the mass number reduces by 4, giving us a brand new element there. Similarly with platinum, atomic number reduces by 2, mass number reduces by 4, gives us osmium 186. Okay, so that's the basic alpha decay series, and that's how you can work out alpha decay for elements that undergo alpha decay. So over to yourselves now. We've got several challenges here. Radon 220, where Z, the atomic number of radon, is 86. Uranium 235 isotope, plutonium 239, to do the maths and work out the decay for those. And then the last 2 are reverses. Really, we end up, this is the daughter, what did we start with? And similarly, you know, what parent produces tungsten? That's what we end up with. Where did it come from for alpha decay? So again, pause the video, have a go at those, write them out, don't just do them in your head, and see if you can write out the decay series for each of those. Okay, so pause the video and have a go at those. Okay, so the answers for these then are radon 220. Radon's got an atomic number of 86, so it produces polonium, 84 atomic number, mass of 216. Uranium similarly goes down from 92 to 90, which is lead, Pb, plumbum, and the mass number goes down by 4 to 231. So we've got lead 231 isotope here. Lots of radioactive things eventually end up as lead, but lead is there. And plutonium 239 ends up as uranium. Okay, by it decaying by alpha emission would then produce uranium 235, which I guess then might go on to decay subsequently as example 2. Going the other way around, if lead is the daughter, lead 207 isotope is the daughter of an alpha particle, what was the parent element? So you reduce the process and add 2 to the atomic number and add 4 to the mass number. So the atomic number will increase from 82 up to 84, which is polonium, and you add 4 to the mass number of that is 211. So the answer will be polonium 211, which we should represent as this, 84 as an atomic number and 211 as its mass number. Similarly with tungsten, same process again. Add 2 to the atomic number, add 4 to the mass number, we get osmium 184, and that's what we should have written down for that. So hopefully you got those right and you understand about alpha decay, which again I think should be pretty straightforward. Now beta minus decay is the beginning of something slightly more challenging for this one, because we now need to refer to beta minus as beta minus decay, and the symbol we give to a beta minus particle is this. It's an electron with a -1 negative charge, because we know electrons are negative, and 0 mass, effectively 0. It's about 1,840th-ish but we count that as 0 for these calculations. The issue is, though, this is all nuclear radiation, so all of these emissions are coming from the nucleus. And until this point, we probably haven't thought you could get an electron out of the nucleus, because a nucleus is only made up of protons and neutrons until this point. Well, this is where everything changes. Okay, yes, we start with protons and neutrons on the nucleus, but it gets a bit more complicated. We have to get an electron out of the nucleus somehow. So how does that happen? How do we get an electron out of the nucleus? And this is where it becomes a bit radical. A neutron turns into a proton and a high energy electron. Okay, so we're converting a neutron with a 0 charge into two other particles, a proton plus and an electron negative. So the charge is equal, no charge to start with, and the positive and negative that we end up with conserve that charge. So this is really fundamental and probably quite radical so far, is that a neutron can change to a proton and an electron. So if we're going to get a beta minus particle emitted, then the neutron changes to a proton, and that's going to change the makeup in terms of protons and neutrons of the radioisotope that we're dealing with. And it looks like this. Carbon-14, for example, the radioactive version of carbon, would decay, throwing out a beta particle, beta minus particle, and producing a new daughter product of nitrogen. And you can see the numbers have changed here, and we'll just talk through that and how those. Okay, so the neutron turns to a proton, and if we take that example on the previous page, what we do is we have the fact that the atomic number will increase by 1 because a neutron has become a proton. So our atomic number of 6 that we started with will increase by 1 to 7, and because the neutron has changed to a proton but they both have the same mass, the mass number doesn't change. So we find out that the atomic number increases by 1, we look it up and you find that 7 is nitrogen, and don't forget we must also add the fact that we've got a beta minus particle emitted as well. You must always remember that you do the conversion bit on this side, but you've got to also add the fact which was the particle that was emitted on these. So yeah, a bit radical this, but beta minus decay, a neutron turns to a proton, so the atomic number increases and we get a new element formed, okay, because it's got a new atomic number, but the mass number stays the same because neutrons and protons have the same mass. Okay, here's some examples that I'd like to have a go at using that methodology from the previous slide. Have a periodic table available because you've got to look up the daughter nuclei. You'll calculate an atomic number, but you need to look it up and see what the element is for those. So we've got actinium, the 228 variety, helium-6 and potassium-42. Pause the video and see if you can work out those on a piece of paper if they undergo beta minus decay. So looking at these, we have actinium. Because it undergoes beta minus decay, the atomic number will increase by 1 and the mass number will stay the same. So we have thorium for that one. Helium, again, the atomic number increases by 1, so we get lithium and the mass number stays the same. And potassium-42, atomic number increases by 1, so we get calcium and still 42 with our beta minus particle emitted. Again, just to make sure we're really good at these things, we write out the beta decay series for these radioisotopes as well. Okay, pause the video and see what you can do in terms of beta minus decay for each of these: phosphorus, cobalt, strontium, iodine, uranium and plutonium. Again, have a periodic table so you can look up what the atomic number of these is and what the name of the daughter product is when you've worked it out. Okay, have a good go at those. Pause the video and we'll reveal all when you're ready. Okay then, so phosphorus 32 would increase to sulfur. Atomic number increases by 1, 16. 32 remains the same, it's just sulfur. Cobalt, mass number stays the same, but that becomes nickel. Strontium would become yttrium, and iodine 131 would become xenon 131. Uranium 238 would become neptunium 93, and plutonium would become americium 239. Again, mass numbers stay the same, but the atomic number increases by 1. In a similar vein, give you a bit of head scratching about this, a positron is a positively charged electron coming out of the nucleus. Okay, same mass as electron but a positive charge, and this is how we reflect a positron in terms of its symbol, +1 as its charge, no mass. Okay, and again what we've got to consider is how do we get this out of the nucleus? Okay, so have a think about that then. From what we've just talked about beta minus, taking that as a model, how do you think we can generate a positive electron out of the nucleus? Okay, so just hit the pause button, have a think about that. When you think you've got it worked out, resume. So, to get a positron, this time we start with a positive particle in the nucleus, the proton, and that turns into a neutron, which stays in the nucleus, and the positron is then emitted. So we're preserving the charge. We start with the positive charge, the proton, and we end up with a positive charge thrown out as the positron, and therefore, you know, charge is preserved, and mass is preserved because a proton weighs the same as a neutron. But because a proton is changing into something else, then the atomic number is going to change as well. We're going to lose a proton and convert it to a neutron. So in terms of writing out positron decay, beta plus decay, it would look like this. The mass number will remain the same, protons and neutrons remain the same, but the atomic number would decrease by 1 because the proton has changed into a neutron, and we're going to get a new element, in this case neon. So sodium 11 would reduce to something with an atomic number of 10, which is neon, and our beta plus particle. Okay, it's lost a proton, so we've got a new element that we need to look up. So similar methodology to beta minus, get them the right way around, is how we work these ones out. So when the nucleus undergoes a beta plus decay, the proton changes to a neutron and a positron is emitted. So how would that, just to sort of see if you've been listening, how would a beta positive emission affect the atomic number? It would decrease it by 1. And how would it affect the mass number? It would stay the same. Okay, and then what would happen when that element undergoes beta plus decay? Palladium, we get this as a nice example of it, where we have the atomic number decreasing by 1 and the mass number staying the same, and the beta particle, beta plus particle, positron, emitted. Okay, and just a quick think about it, what happens during neutron decay? Okay, that's the other type of decay we need to know about, and it's as simple as it throws out a neutron from the nucleus, and therefore the mass number reduces by 1, everything else stays the same. Okay, so on your own, pausing the video and writing them out, what is the positron decay equation for those radioisotopes, a radioactive version of magnesium and a radioactive version of iodine? Okay, so pause the vid and write down what you think those would look like if they went to go positron beta plus emission. Okay, and we should see that magnesium has reduced its atomic number to 11, which is sodium, mass stays the same, and iodine has reduced its mass number to 52, which is tellurium, and that remains the same as 121 mass number with beta plus. Okay, so we've got those sorted out. Pause again, we're getting the hang of this and getting the way we work with these, and write down the nuclear equations for those elements that have undergone positron decay. Okay, pause the video and do the maths, write them out. And the answers are as follows. Iron goes to manganese, fermium goes to einsteinium, polonium goes to bismuth, and radium goes to francium. Okay, just following the same rules for all positron emissions, beta plus decay. Gamma decay, again, gamma is a wave of energy. It's not a particle in any way, so it's not actually sort of throwing anything solid out or actually fundamentally changing what is in the nucleus. But if you imagine a bag full of marbles, okay, you can roll them around, can't you? You can move them, they can slide over each other, and they can repack and rearrange themselves in different ways. And that's basically the model of how gamma rays are emitted. Okay, when the nucleons rearrange, these nucleons, the protons and neutrons, when they rearrange to pack in a slightly different way, that has a different energy level associated with it. So if you rearrange your bag of marbles and squash them into a different form, then that is likely to have a lower energy state, and some of that energy has to be given out in one way, and that is as gamma rays. Okay, so there's no change to the nucleus for these. What's in there stays exactly the same. So no new element is formed, but the particles in the nucleus sort of repack themselves, rearrange themselves to form a lower energy state, a more stable state, and that energy's got to go somewhere, so it's given out as gamma decay, gamma ray. Okay, and what that usually happens as in association with other decay. So you have your first decay series, such as cobalt to nickel here, but that's still unstable. So you've got your decay there by beta minus emission, because the atomic number has increased, but that nickel on its own is still unstable as it is. So what happens, that nickel then gives out the gamma ray to help stabilize itself. It doesn't change what it is, it's still 2860, but this is not quite stable, so it gives out a gamma ray and becomes more stable, so it's happier with that. Okay, so again, gamma rays usually emitted associated with other types of radiation, rather than just on their own randomly. Something happens, a particle, alpha, beta or positron emission takes place, and then to sort of finally stabilize itself, a gamma ray or gamma rays are often given out after that, just to result in additional stability.